Hello and welcome to the video. We're going to share our final project of IoT. And our group consists of four people. With me, myself, Raffie, as the leader, and the developers are Melvin and Faris, and the designer finally is Ash.
First, we would like to explain about the abstract. So our report explored the design, implementation, and evaluation of a traffic system using CupCarbon simulation. And the system uses a wireless sensor network simulation to simulate traffic flow. The aim of our simulation is to improve urban traffic management efficiency and adaptability by incorporating real-time crowdedness data in the decision-making processes. So uh, in our Internet of Things project of carbon that we do consists of several phases. And then what we did is that we research a problem that can be taken as a case to solve. And then we find the solution for the problem and attempt to implement that solution in carbon. Our first and initial idea was a traffic system for emergency vehicle, but due to limitation on carbon, the solution cannot be implemented fully. And as a result of this, we created a new idea of another simulation called a traffic system based of crowdedness. And that is the simulation that we developed and implemented on carbon. And in short, based on what I explained earlier, the system allows the improvement of urban traffic management efficiency by incorporating real-time crowdedness data in the decision-making process. And our simulation consists of several elements, and these elements are vehicle detectors, receivers, and traffic light. And the vehicle detector serves as a sensor to detect the presence of a vehicle inside the detector radius, and acting as a transmitter, the receivers acquire the data from the detectors and pass it to the traffic light or traffic management system. So, in summary, for our abstract, our basic simulation explores the advantages and challenges of using crowdedness data in traffic management. And while simplified, it also provides a foundational understanding of the concept's potential benefits. And these findings set the stage for more advanced simulation and potential real-world application and future research. And for the methodology, I will leave the stage to Rafi.
Okay, thank you, Faris. So this is our methodology for doing our final project. So in our idea of the project, for the system, we're gonna have our sensors on first, and then the sensors are going to detect on to the vehicles that are going to arrive on the lane. So when the vehicles arrive on the lane, they will receive the input, and then the sensor will check if the lane is full or really, really dense in traffic. They will send action to the central node and then toggle green light and then regulate traffic until it reaches the normal density. And if it's not, they will ignore it and regulate traffic at normally. And then that's the end of the system. So for the simulation layout itself, I'll leave this to Melvin.
So for the simulation layout, we have a few types of vehicle detector, two types of vehicle detector, and one central node that controls all the traffic lights, and of course the traffic lights themselves. So here we're using mobiles as a stand-in for cars. And as we can see in the first script for the vehicle detector, the vehicle detector, the first vehicle detector, uh, is supposed to detect a car if there is a car in front of the lane, and then it'll send a signal to the vehicle detector in the back, which is the second vehicle detector. Now, the second vehicle detector compares the signal it gets from the first vehicle detector and the signal it generates from what it's seeing on its own. And then if both signals say that there is a car on both ends, the vehicle detector will send the signal to a receiver, which basically forwards it to the central node. Now, in the central node, we can see that it just has a lot of is basically a table of orders for each of the traffic lights. So, for example, if it receives order 1, it turns on traffic light number 29 with the ID of 29. And then if it has order 2, it turns on the traffic light with the ID of 30. And then so on and so forth. And then, of course, the traffic lights themselves can turn green, or they can also turn red. Now, if there are no priorities that we need to fulfill, we should have it on a continuous cycle. So here are some of the simulation results. So we can see that if we look at the first frame of the simulation result,
The
the
first simulation result, the sensors detect vehicles in a lane and reads it, right? If it's occupied and heavy in traffic, then next one, since lane 1 has more vehicles than lane 2, sensors from the first lane transmits the central node to accommodate lane 1's busy traffic. Following are also screenshots showing it. Result shows the busy lane was given the green light to minimize traffic density. The problems we encountered during the creation of the simulation was CupCarbon lacking in resources in the application, and also our inexperience with CupCarbon, and also the outdated program causing multiple crashes when running the simulation. In conclusion, this paper visualizes traffic systems designed as an IoT environment. Using CupCarbon, we were able to imagine and execute an automated traffic system that takes data and executes it with its own decision-making system. The simulation uses nodes and sensors to detect occupied lanes and execute traffic systems when needed. This paper discusses the difficulties of using CupCarbon itself as we try to adapt. That's all for our group. Thank you so much for your attention.